What you are about to see and hear may seem very strange. It may cause your eyes to cross and your toes to curl and uncurl convulsively. You may feel compelled to pull out your hair or use the bathroom. Should you experience these effects, don't panic.
Azimuthal quantum number, titration, ZIMS, antibody, gimbal, electron, stoichiometry, mole fraction, beryllium, bobinium, lithiation.
Remember this. Chemistry looks and sounds strange because chemists have developed their own special language, which they use to describe things. So, learn the language. Study the terms. Once you get used to the way chemistry sounds, you won't feel like it's causing a nuclear meltdown in your head. In no time, it will all make perfect sense.
Alas, no more delay. Let's get right to the heart of the matter.
Now we're ready to find the molar mass of a substance. This process is going to look real familiar. Now remember the difference here. Molar mass refers to the mass of 1 mole of molecules. Molecular mass is the mass of 1 molecule. Let me say that again. Molecular mass is the mass of 1 molecule. The calculation for molar mass looks exactly like the calculation for molecular mass, but the molar mass is always expressed in grams per mole, since we are, in fact, dealing with an entire mole.
The molar mass of water molecules, which is the mass of 1 mole of water molecules, equals the mass of 2 moles of hydrogen atoms plus the mass of 1 mole of oxygen atoms. So, we will add 2 times the atomic mass of hydrogen plus the atomic mass of oxygen. That's 2 times 1.0080 grams per mole plus 1 times 16.00 grams per mole. 2.02 plus 16.00 equals 18.02. So, the mass of 1 mole of water molecules, known as the molar mass, is 18.02 grams per mole. Why? Because the numbers you use for AMUs and grams per mole are the same.
So, use grams per mole in calculations, whether you're calculating molecular mass or molar mass. It's that simple.
Section D, percent composition.
The percent composition of a compound gives the ratio of elements that make up the compound. In other words, it specifies what percentage of the total compound each component element represents. The compound glucose is made up of carbon atoms, hydrogen atoms, and oxygen atoms. So some percentage of the glucose is carbon, some percentage is hydrogen, and the remainder is oxygen. Using another handy-dandy chem formula, we can figure out these percentages.
Here's the formula. Take the number of atoms of one element in a molecule, multiply it by the element's atomic weight, divide that quantity by the molecular weight of the compound, then multiply the whole deal by 100. To find the molecular weight, add up the masses of the component atoms the same way we just learned. Now let's find the percent composition of the elements in the compound glucose.
First, let's find the molecular weight of glucose. Like we did before, we'll express the weight in grams per mole. Remember, it's easy to find each element's weight in grams per mole. You just look up each atomic weight in AMUs in the periodic table and change the AMUs into grams per mole. So here goes. The 6 carbon atoms in glucose multiplied by the atomic weight of carbon, 12.01 grams per mole, equals 72.06 grams per mole. 12 hydrogen atoms times the atomic weight of hydrogen, 1.008 grams per mole, equals 12.10 grams per mole. And 6 oxygen atoms times oxygen's atomic weight, 16.00 grams per mole, equals 96.00 grams per mole. Add those 3 products together, and we get the molecular weight of glucose, 180.16 grams per mole. For our calculations, we'll round our answer to 180.2. Bingo! Now let's find the percent composition of glucose.
We'll find the percentage of carbon first. There are 6 carbon atoms in 1 molecule of glucose, so take 6 times the atomic weight of carbon, which is 12.01 grams per mole, divided by the molecular weight of glucose, which we just figured out is 180.2 grams per mole, all times 100. Taking the math one step at a time, we multiply 6 atoms times 12.01 grams per mole, and we get 72.06 grams per mole. 72.06 grams per mole divided by the molecular weight of glucose, 180.2 grams per mole, equals 0.39988. There. Now to get this as a percentage, we just multiply it by 100. Rounding our answer off to 4 significant figures, we find that glucose is composed of 40.00% carbon. Cool, huh?
There are 12 hydrogen atoms in 1 molecule of glucose, 12 times the atomic weight of hydrogen, 1.008 grams per mole, divided by the molecular weight of glucose. That's 12.096 grams per mole divided by 180.2 grams per mole times 100. Dividing 12.096 by 180.2 gives us 0.067125 times 100. We can only have 4 significant figures in our answer, which works out to be 6.713. Glucose is 6.713% hydrogen.
On to oxygen. We'll fly through this one since I'm sure you've gotten the hang of this by now. 6 oxygen atoms times 16 grams per mole equals 96.00. 96.00 divided by 180.2 grams per mole equals 0.5327. 0.5327 times 100 equals 53.27. The compound glucose is 53.27% oxygen.
The great thing about percent composition problems is that it's easy to check yourself once you think you've found the answer. We just figured out that glucose is 40.00% carbon, 6.713% hydrogen, and 53.27% oxygen. So, theoretically, all of our percents should total 100%. If we add 40.00, 6.713, and 53.27, we get 99.98, which is pretty darn close to 100. So, we got it right.
Now I think we'd like some complete utter foolishness. Much better.
Section E, empirical formulas.
Empirical formulas show ratios rather than exact quantities. On the other hand, a compound's molecular formula tells you the exact number of each type of atom in 1 molecule of the compound.
For example, hydrogen peroxide's molecular formula, H2O2, tells you that each hydrogen peroxide molecule consists of 2 hydrogen atoms and 2 oxygen atoms. Hydrogen peroxide's empirical formula, HO, only tells you the ratio of hydrogen to oxygen in a hydrogen peroxide molecule.
Same deal with glucose. Its molecular formula, C6H12O6, tells you that each glucose molecule consists of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. The empirical formula for glucose, CH2O, tells you only the ratios of atoms in a glucose molecule. The subscript 2 in the empirical formula doesn't mean 2 atoms like it would in a molecular formula. It means twice as many, indicating a 2-to-1 ratio of hydrogen to the other components, oxygen and carbon.
In many cases, a molecule's molecular formula is the same as its empirical formula.
Yeah, the same.
Like in the case of CO2, carbon dioxide. Each carbon dioxide molecule has 1 carbon atom and 2 oxygen atoms, and the ratio of oxygen to carbon is 2-to-1.
Earlier, we talked about percent composition, which expresses the ratio of the elements that make up a compound by specifying what percentage of the total compound each component element represents. We can take the information about the percent composition of a compound and use it to find the empirical formula of the compound. Here's how.
We have 100 grams of water. Let's say we've already calculated percent composition, like we did earlier for glucose. And we know that water is made up of 11.19% hydrogen and 88.81% oxygen. Since we have a 100-gram sample, conversion to grams is easy. 11.19% of 100 grams is 11.19 grams of hydrogen, and 88.81% of 100 grams is 88.81 grams of oxygen.
We have to find out how many moles of hydrogen atoms we have, because to determine the ratio of hydrogen to oxygen, we're going to compare how many moles we have of each element. We'll convert from grams to moles, changing the units with the unit factor method. Convert from grams to moles by multiplying our sample of hydrogen, 11.19 grams, times 1 mole of hydrogen atoms over the mass of 1 mole of hydrogen, which is 1.008 grams. What we're doing here is the unit factor method. Remember Willie the wild worm?
Hey, babe.
We want to change units from grams to moles, but we don't want to change the amount of our sample. Multiplying our sample, 11.19 grams, by 1 mole of hydrogen atoms over the mass of a mole of hydrogen is like multiplying by 1. So it changes units without changing amounts. See, if you weighed out 1 mole of hydrogen atoms, it would weigh 1.008 grams. So in effect, 1 mole of hydrogen atoms and 1.008 grams of hydrogen are the same thing. That's why it's like multiplying by 1. 1 mole of hydrogen atoms over 1.008 grams of hydrogen multiplied by our 11.19 gram sample of hydrogen gives us 11.10 moles of hydrogen atoms.
Now we'll convert our sample of oxygen from grams to moles. 1 mole of oxygen atoms has a mass of 16.00 grams. So 1 mole of oxygen atoms over 16 grams of oxygen times our 88.81 gram sample of oxygen gives us 5.551 moles of oxygen atoms.
So let's look at the ratio of moles of hydrogen atoms to moles of oxygen atoms. The ratio of moles of hydrogen to moles of oxygen is 11.10 to 5.55, or 2 to 1. For every 2 hydrogen atoms, there is 1 oxygen atom in our compound. So water's empirical formula is H2O.
Empirical formulas come in handy when we work with substances that don't consist of molecules, like water and glucose. We obviously can't calculate a molecular mass for substances that have no molecules, because they have no molecules. Instead, we calculate a formula weight, which is simply the sum of the masses of the atoms in the empirical formula.
Sodium chloride, aka NaCl, aka ordinary table salt, is a crystal, not a molecule. Since sodium chloride is not a molecule, we can't calculate its molecular weight. We have to calculate its formula weight. Crystals are different from molecules because crystals don't have definite pairing and bonding of atoms or ions like molecules do. Crystals are more like a bunch of atoms or ions stacked up to one another, like the bricks in a building. The atoms or ions forming a crystal stack up on each other in a repeating pattern to form what's called a crystal lattice.
No, not lettuce. Lattice.
So, formula weight and molecular weight are almost the same thing. But formula weight finds the weight of atomic structures which are not molecules. Finding formula weight is very easy. The process is the same as you use to find molecular weight, but you base your calculation on the number of atoms indicated by the structure's empirical formula, rather than on a molecular formula. We'll demonstrate by finding the formula mass of NaCl.
So, to find the formula weight of sodium chloride, start by looking up the masses of sodium and chlorine in the periodic table. The mass of sodium is 22.9898 AMUs, and the mass of chlorine is 35.453 AMUs. Again, we'll use the cool rule that 1 mole of any type of atom has a mass in grams equal to the atom's mass measured in AMUs, and we'll show these values in grams per mole by putting the grams per mole after them.
So 22.9898 grams per mole plus 35.453 grams per mole equals 58.4428 grams per mole. But this is not our answer.
Now don't forget the rules for sig figs with addition and subtraction. Your answer can only have as many decimal places as the term in the problem with the fewest decimal places. The mass of chlorine, one of the terms we added, only has 3 decimal places, so our answer can only have 3 decimal places. The formula weight of sodium chloride is 58.443 grams per mole.
Introducing for the first time ever a way to determine your weight. Yes, now you too can instantly know the weight of the combined atoms and molecules of your body. How? With this. Here's how this amazing product works. First, step up to the device. Second, lift your feet to stand upon its platform. And third, read the numbers and hate the results.
Empirical formulas only show you the ratio of atoms in an atomic structure like a molecule or a crystal. We base the weight of atomic structures, like crystals, which are not neatly bonded like molecules, on the combined sum of the masses of the atoms in the empirical formula. This measurement is called the formula weight.
Section F. Problems based on chemical equations.
To calculate the masses of substances taking part in a chemical reaction, follow these 4 steps.
Hey, look, I can see my reflection in the trash.
How appropriate.
First, write the balanced equation for the reaction. Next, convert the known mass of one of the reactants or products to moles. Then, use the balanced equation to set up the appropriate conversion factors so you can find the number of moles of the other reactants or products. Finally, convert your values from moles back to grams.
Oh, it's time for my favorite TV show.
Welcome to the Cooking with Professor Rowley Show.
Hi, welcome to Cooking with Professor Rowley. I'm your host, Bink Shoemaker. Hi, how you doing? Good to be here. Okay, on today's show, our incomparable culinary chemist is going to whip up a tasty batch of magnesium oxide. Okay, yeah. Let's welcome the professor to the show. Hey, Professor, come on out here.
How you doing, Bink?
Good to see you.
Good to be here.
I'm glad you are. So, Professor Rowley, tell us the secret of your famous magnesium oxide.
Well, I start with fresh magnesium in ordinary laboratory air.
Nothing but the best.
Then I gently charbroil the magnesium over the Bunsen burner.
Ooh, flambe! All right.
You know it's done, Bink, when it turns a lovely white.
Ah, look at that.
With the addition of heat from the Bunsen burner, the magnesium has reacted with the oxygen in the air to form magnesium oxide.
Yeah, magnesium oxide. And doesn't it look tasty? I like mine with a little bit of horseradish.
Just for kicks, let's say our incomparable culinary chemist started out with 2.4 grams of magnesium and an unknown quantity of oxygen floating around in the genuine laboratory air. How many grams of magnesium oxide did he produce from this reaction? If you were to do this experiment in your kitchen, you could just weigh the magnesium oxide you produced. But it's pretty cool that you can calculate how much of a product you can expect to get from a reaction without even doing the reaction. Here's how.
First, look at the balanced equation for the reaction. It says that 2 moles of magnesium reacting with 1 mole of oxygen yields 2 moles of magnesium oxide. In other words, if we start with 2 moles of magnesium and 1 mole of oxygen, we will end up with 2 moles of magnesium oxide. So the number of moles of magnesium that we start with will equal the number of moles of magnesium oxide that we end up with.
You young whippersnappers are so full of talk. Prove it.
Oh, they can prove it, Granny. Just watch. They can prove it. We sure can, Granny. Here comes step 2. Convert the known mass of one of the reactants to moles. We'll find out how many moles of magnesium there are by multiplying the weight of our sample of magnesium by 1 mole of magnesium divided by the weight in grams of 1 mole of magnesium. 1 mole of magnesium over 24 grams times 2.4 grams equals 0.10 moles of magnesium. Convenient, huh?
On to step 3. Now we'll find how many moles of the product magnesium oxide there are by setting up a conversion factor. We base the conversion factor on information from the balanced equation. So here's the conversion factor. We'll multiply the number of moles of magnesium we have, which we just calculated, by 2 moles of magnesium oxide over 2 moles of magnesium. Why? Because multiplying by 2 moles of magnesium oxide over 2 moles of magnesium changes our units without changing quantities. It's the unit factor method again. Multiplying by 2 moles of magnesium oxide over 2 moles of magnesium is like multiplying by 1, because the balanced equation for the reaction says that for 2 moles of magnesium, we get 2 moles of magnesium oxide. Cancel out the moles of Mg on the top and bottom, and that gives us 0.10 moles of magnesium oxide. And there it is, just like we told you. We have 0.10 moles of magnesium oxide.
Hey, Granny, now they're going to convert to grams. Look!
Now, to find out how many grams of magnesium oxide we have, multiply the number of moles of magnesium oxide, 0.1, times the molecular weight of magnesium oxide. The molecular weight of magnesium oxide is the sum of the atomic weights of magnesium and oxygen. So just look up the atomic weights of magnesium and oxygen in the periodic table. Add them up and you'll have the molecular weight of magnesium oxide. So here goes. The atomic weight of magnesium, 24.3, plus the atomic weight of oxygen, 16.0, equals 40.3. So 40.3 is the molecular mass of magnesium oxide.
Now let's find the mass in grams of MgO. 0.1 moles of MgO times 40.3 grams per mole equals 4.0 grams of magnesium oxide.
Step 1. Write the balanced equation. Step 2. Convert the mass of one of the reactants to moles. Step 3. Use the balanced equation to set up the right conversion factors so you can find the number of moles of other stuff you have. And step 4. Convert from moles back to grams.
A mole is a unit of measurement that represents 6.022 times 10 to the 23rd atoms, molecules, or other small things like that. This number is known as Avogadro's constant. The atomic mass of an element is the mass in grams of 1 mole, that is the element's atoms. You can look up the atomic masses of atoms in the periodic table, which gives the atomic number in atomic mass units, or AMUs. Molecular weight is the combined mass of the group of atoms forming a single molecule. To find the molecular weight of a substance, simply add the atomic masses of the atoms that form the molecule. Formula weight finds the weight of atomic structures which are not molecules, like crystals. The percent composition of a compound gives the ratio of elements that make up the compound. In other words, it specifies what percentage of the total compound each component element represents. Once you know the percent composition, you can write a molecular formula, which tells you the exact number of each type of element in one molecule of the compound. You can also write an empirical formula, which shows ratios rather than exact quantities.
Part 4. Solution Stoichiometry.
You remember that a solution is a homogeneous mixture of 2 or more substances. In all solutions, there's a solute and a solvent. The substance present in the largest amount is usually referred to as the solvent, and the other substances are referred to as the solutes. So, for the blue dye solution we talked about earlier, the water was the solvent and the dye was the solute. In a solution that consists of a solid and a liquid, the solid is always called the solute and the liquid is always called the solvent.